So, hello everyone. My name is Uhlig from the Technical University in Darmstadt, Germany. Together with my supervisor Thomas Göbel from Hochschule Darmstadt in Germany and Harald Baier from the Bundeswehr University in Munich, we looked into ways to efficiently and effectively identify IoT devices based on their traffic flows through the use of approximate matching algorithms. Now, approximate matching algorithms, you might have heard of them as fuzzy hashing algorithms. Those are similarity preserving hash functions. So in contrast to cryptographic hashes, which sort of change as soon as a bit flips. So no two images that are just slightly different have the same hash. Approximate matching hashes or fuzzy hashes can in fact show you which artifacts are very similar. They were introduced in the early 2000s in order to deal with spam and forensic challenges and string matching and stuff like that. They're rather simple to implement and rather resource efficient. And over the years there has been a plethora of algorithms, whether it be context-triggered piecewise hashing statistically, or hashes that are based on statistically improbable features, block-based rebuilding, whatever. All these algorithms have in common that they work in a sort of three-step way. So first of all, there's a feature selection phase where we can select special features of the artifact that we want to match. Then there's a digest generation phase, so where we generate the digest, the hash, and then we can compare this hash with other hashes and then assess how similar two artifacts might be. Over the years, there have been, as it was previously said, a lot of algorithms. The most well-known one might be TLSH, which is currently in use by Google, and yeah. In Google's VirusTotal. We have MRSH, SD-hash, and SSDeep. All these algorithms stem from sort of scientific research and are sort of publicly well documented. TLSH is publicly documented as well, but is sort of like the only one that is actively developed by the private sector. And yeah, these algorithms are answering demand or are sort of answering a lot of challenges. So they are able to detect similar objects. They are able to cross-correlate, so say how similar different files might be or how much sections they might share. They can detect embedded objects. So if you've got an HTML page with some pictures in it, they might be able to say, well, okay, there are those and those pictures in it. And they're able to detect fragments, of course. Might that be malware in a file? Might that be other stuff? And our specific area of interest was network forensics and especially IoT traffic flow identification through these algorithms. The basic idea is you have an IoT network, and this IoT network emits sort of packets, or the devices within it might emit packets. You hand them over to the algorithm, and the algorithm is able to determine, okay, this trace stems from IoT camera, another trace might stem from a washing machine, and a third one might stem from a Fitbit or a wearable. The idea is based on a publication by Charayev and Goons from 2021. And the basic idea of their research was that you take the activity of a device and you select a certain sample from this device. And this sample serves as a filter. So their Elsif architecture is handed over this little filter. And through this filter, it can determine, as we previously saw, which hash sort of other incoming traces belongs to which device. And the highest scoring samples are sort of considered positives. Yes. And our motivation was really to see whether we could do better in the field. So we've got experience with another well-documented approximate matching algorithm, which is called MRSH-CF. MRSH stands for multi-resolution hashing, and CF stands for cuckoo filter. It is more of the MRSH is a very traditional approximate matching algorithm, and the cuckoo filter makes it very fast. It's very easy to scale. We've done some research on how to detect file fragments in network traffic, and we were able to get our detection rate up to 4 gigabytes per second. And we looked onto this challenge of device identification through IoT traffic traces very optimistically. And first of all, there's a bit of a difference. So the Elsif algorithm that we were able to reproduce in coordination with Shariyev and Kunz works a bit different. There's all these filter hashes in the Elsif architecture that stems from different devices. There are all these incoming traces. And the Elsif architecture is then able to determine, all right, the incoming traces might belong to 70, with a security of 97% to device X. And the highest ranking device then is determined to be the device of origin. They incorporate either TLSH or NIL-SIMSA in their architecture, which are both at least significant bit hashing algorithms. And with CU IoT, which is our architecture, which incorporates MRSH-CF with cuckoo filter, there's a little different working. So all the incoming traces are sort of associated with the filter. And we do a sort of relational ranking. So we say, all right, if we have sort of most parts of a very small device trace that counts higher than if we have, for example, of a device that emits a lot of traffic and we only have a small fraction of it. But there's more, then we have a higher confidence. So it's a bit of a relational ranking in that way. And early on we did a very short performance test and were able to see that our implementation of Elsif with NIL-SIMSA and TLSH performed a bit faster. TLSH, developed by Trend Micro, was king of the hill. It was very, very fast. It also, as we can see in model size and feature size, it doesn't take up very much space for the filter, and it has a rather quick response time. MRSH-CF has a rather quick response time as well, but it's just about battling for second place with NIL-SIMSA. For the tests, we used 3 data sets. We used the setup data, which stems from Mittinen et al., consists of 23 devices, and every device setup phase is recorded, and this recordings is then put into this data phase. And the filter size that we used for the experiments amounts to 5% of each of the overall traces of every device. The same with idle, 56 devices, overall 2.33 days per device, and the filter amounts to, in this case, 29%, because idle produces a lot more sort of very uniform traffic. By Rand and Dubar is the original data set, then 22 devices from the active data set collected over 20 days by Shariyev and Kunz themselves. And first of all, let's start with the active data. And right off the bat, we see that CU IoT was more successful than its competitors, Elsif, that either incorporates NIL-SIMSA or TLSH. Filter accounts for 3.4% of the device's traffics, and we were able to see that our solution with CU IoT outplayed its competitors with regards to devices that produce only a very, very small footprint, and that overall in their active phase produce a very, very, very sort of tiny amount of traffic. As we can see here in this confusion matrix, which shows on the left side the device traces and on the bottom the device filter. So it shows you, for example, here on the left, it shows you how good chime doorbell, making up the filter, was able to detect chime doorbell traces. And what we want to see is sort of this line of blue here, which basically shows us that the highest, if we give the algorithm the filter of chime doorbell, it is actually able to detect chime doorbell traces with the highest confidence. And especially for devices like TP light bulb, or in this case Gumia coffee maker, which emits very, very small amount of traffic, we were able to do considerably more, we would say, than Chayev and Goons with Elsif. Our second test with setup data. The filter accounts for 5% of the device traffic. What we saw right off the bat, still CU-IoT has the best performance metrics. However, we saw that the visibility decreased considerably when we had a lot of devices that stem from the same vendor and might have the samey protocols. And also for this setup data, we actually have data from AI-based approaches. So this is some. What we see here in this picture is the accuracy that was sort of collected, not only from TLSH, this is what we did with Elsif and CU-IoT, which is our own approach, but also with Elsif, which is in this case Elsif with Nesima, not with TLSH, and other approaches from other papers that produced algorithms like IoT Sentinel, OSVM, SSID, and EE. Those are all sort of device identification approaches that focus on setup data for the identification. And the red line here is CU-IoT, and the blue line here is TLSH. And as you can see, they are mostly battling for the first place here in terms of accuracy overall device. The CU-IoT is slightly better, but we see a slightly better performance than these AI-based approaches. However, as I told you before, there is a confusion from within devices that stem from the same vendor. This is a very significant finding in this trace. Then we have a third test with idle data. The performance metrics for idle data show that Nilsimsa, Elsif Nilsimsa, versus CU-IoT is very close, but Nilsimsa performs in some incidences better. This is very interesting because idle data that is rather homogeneous. So we have 112 hours of recorded traffic for each device. As you may recall, for active data, we had like over 20 days. So it's a bit smaller. But also, we saw a lot of devices that in their idle phase basically produce nothing but a short keep alive or something like that, just a short ping or something. And there's a great variation between those devices on how much data they ultimately emit. Some of those devices might only produce in their whole idle lifetime might only produce a few bytes, and others might produce a few megabytes. For the ones that produce only a few bytes, CU-IoT is actually not very good at determining these. And also, like devices that stem from the same vendor, we have a very wide array of devices, in this case 55 devices. CU-IoT is still got a bit of catching up to do. The TLSH data in this case stems from Chayev and Goons. We were not able to fully replicate the results for this setup. But yes, we were in contact with Chayev and Goons, and we are very confident in the data. And, so this is why we used them here. So the conclusion is that CUI presume performs best in 2 out of 3 data sets, and then the third one is very, very close to Nilsimsa. Idle data remains a challenge. Maybe there has to be done a bit more research how we can optimize this. We believe that the relational ranking that I presented to you in one of the earlier slides might be can be a bit improved upon. Also, COIoT's strengths and weaknesses is that we were for the first time able to correlate very small fragments of very small traces in active data, not in idle data though, and that if that these traces are very homogeneous, like we see in idle data, that this could still present a problem. This is sort of a slight caveat. Differentiating between similar protocols, same devices remains a challenge even for the other algorithms, but still is not fully developed. And something, just a smaller thing, is that we think that Elsif is much easier to implement than COIoT. We have a lot of experience with the algorithm, but as Chayev and Goons told us about their algorithm, how they actually did it, it's become very apparent that it is sort of better. However, COIoT, we are very confident, is able to scale better. So if you might apply our research for, let's say, something that has over 1,000 devices, a cuckoo filter like COIoT has it is much better, we believe. Yes, so our contributions, or we reassessed previous research in a much broader way and sort of developed a broader use case for approximate matching algorithms beyond just simple forensic evidence assessment. We achieve between 83 in our worst case and almost 100% of the classification performance. And yeah, we will put up research, we will make it open source, and we will publish it under the link that you can see here. So our current work and further research, we're currently working on ways to optimize the algorithm, to make it a bit more accessible, and to look into ways to make setup data correlation a bit more reliable. And one of the ongoing researches that we are currently focusing on, which is very exciting, is that we see these sort of hashes as a natural language problem. So we take the hashes and we work them over into embeddings, and then we give them over to a multi-layer perceptron or transformer. And this way we can actually detect certain sequences in the hashings, which then will indicate maybe malware or similar things. This is something that has already been done in malware research, and we are now looking into it, whether it can be of use in IoT device traffic device scenario. So come to an end now. This is our bibliography. If you have any questions, feel free to contact us on Thomas Göbel at HDA, Frieda Uhlig here in the middle, or my colleague Harald Baier from Universität in BW. Thank you very much and have a good evening.